Or hello.
Yeah. Yes. So I'll
Uh,
just good afternoon, everyone. We'll just give a small introduction of very small introduction of the speaker. We little got late because of some internet glitches. So we have today with us Dr. Ronak Patel. He is presently working as assistant professor, chemical engineering department, LDCE Ahmedabad. He has a total of 10 years of academic experience. His area of specialization is process modeling, simulation, and catalysis. So his credit is 5 journal publications and 10 conference proceedings. And his area of thesis research is basically studies on hydrogen production via biobutanol reforming for SOFC and EMFC applications. Over to you, Ron.
yes, sir.
Yes, you can start, Ronak.
My screen is visible to you.
Yes, it is visible.
Okay. So first of all, I am very much sorry for the trouble because my internet was down for certain reasons, so I was not able to join in a time. So first of all, I would like to thank management of Parul University for allowing me for this particular session, and especially thanks to HOD Chemical and Professor Priya Saxena for arranging this lecture. So without wasting much of our time, I will be starting with my talk, which is reactor simulation in Aspen Plus, and I would be covering the case studies on esterification and steam reforming reactions. So why I have chosen the reactors, basically because the reactors are the heart of chemical industries. Because if we see the general anatomy of any chemical process industry, it is first step, that is a physical step, followed by a chemical step where the molecules loses its identity and convert into the more useful products. And after the chemical treatment step, again we need to separate out the products, byproducts, and unconverted reactants. So if we design our central part, which is a chemical treatment step, which is the heart, or rather in that particular step, we have a reactor. So if we design our reactor properly, so it may happen that it can take any raw materials which not require any kind of purification, and it will give us the 100% pure products. So that is going to be the idealized scenario. So ultimately, if we design our reactor properly, then we can minimize the physical treatment step, which is pre and post of the chemical treatment steps. So now how we can use this Aspen Plus? Aspen Plus, as you already know, that it is a market leading process modeling tool for conceptual design optimization and performance monitoring for the chemical, polymer, specialty chemicals, metals, minerals, and coal power industries. So what we are going to cover, we are going to cover starting with the introduction to reactor modules, which are based on the stoichiometry, yield, equilibrium, minimization of gift spray energy, and kinetics of reactions, which is CSTR, PFR, and batch reactor. Starting with the first reactor module, which is the R-stoic module. So in R-stoic module, which is working on the stoichiometry of a reaction. So for this module to be used, we need to know the stoichiometry, and when to be used this, when the kinetics is not available, rather it is not important. Taking an example, if we have a acid-base reaction, which is quite spontaneous in nature, and we don't bother about the kinetics of a reaction in that particular reaction. So we require, if we need to simulate that, and we are not also worrying about the thermodynamics or kinetics of a reaction, we should go for this R-stoic module. R-stoic module, at least it requires one input stream and one output stream. That is a mandatory requirement. R-yield, that is going to use the again, it is based on, it do not require a stoichiometry of a reaction, unless like R-stoic, which requires the stoichiometry requirement. The yield in this reactor module, that is defined basis on, rather on a mole basis or a mass basis, which is a mole or mass of a component per total mass input of the block. Again, for this R yield, we it does not consider the thermodynamic feasibility of a reaction, or rather it will also not require the kinetics of a reaction. Basically, R stoic and R yield, that are the reactor modules where we just need to, it will not check the thermodynamic feasibility. For example, if we take an example of a water splitting, H2O will give H2 plus half O2. That is not possible at a room temperature and pressure condition. But if we feed that particular stoichiometry to R yield or R stoic reactor, in that case also it will give us the result depending upon our inputs. So it will not also check the feasibility of a reaction. R equilibrium on the other end, that will check the feasibility of a reaction. It will also check the vapor liquid equilibrium. So for this, we require at least one input and two outputs are required. Two outputs that will give us the vapor and liquid composition. R Gibbs, that is again, it is based on the equilibrium, minimization of Gibbs free energy, and it will give us the composition at the equilibrium. But the advantage of using this R Gibbs is that it do not require any kind of a stoichiometry, whereas the previous module, which requires the stoichiometry and yield of a reaction. RCSTR and R-plug, those are the rigorous reactor modules, because we know that these two are the steady state models and it requires the stoichiometry as well as the kinetics of a reaction. For RCSTR, we have the at least one input and one output that is required. For our R-plug, only one input that is allowed, because we cannot have a multiple feeds in case of a plug flow reactor, and one output that is there for R-plug reactor. R batch, unless like RCSTR and R batch, that is also R plug. This is also a rigorous reactor, but only the difference between them is earlier two was the steady state reactors, and now this R batch, that is unsteady state reactor. Just summarizing this, R stoic and R yield, that are not considering the feasibility of a reaction. What R stoic requires, that is stoichiometry that is required. Kinetics and it is not rigorous model, because it is not also considering the thermodynamic feasibility. Feed, that any number of feeds that we can introduce to R stoic. R yield, that do not require stoichiometric kinetics, or it is also not a rigorous model. R equilibrium, it requires R equilibrium and R Gibbs, both are based on the working based on the thermodynamics. It will check the thermodynamic feasibility of a reaction. For R equilibrium, we require a stoichiometry, and it will also not require the kinetics. Also, it is not a rigorous model, but it can handle any number of feed stream. R Gibbs, on the other hand, do not require stoichiometric kinetics of a reaction. Moreover, it can also handle the any number of feed stream. RCSTR, that is a rigorous, so it requires stoichiometry and kinetics of a reaction. R plug, that is also requires stoichiometry and kinetics of a reaction. On the other hand, feed, that is to R plug reactor, that is only limited to one. And R batch, that again, it is a rigorous model, so requires stoichiometry, kinetics of a reaction, and also for this feed has to be only one stream. Now, taking the first example of esterification reaction, ethanol plus acetic acid, that will give us ethyl acetate plus water, and this are we what this is what we are going to see in a Aspen plus simulation. We are going to compare this different models, which is R stoic, R equilibrium, R Gibbs, R CSTR, and R plug, for the same amount of input, and the reaction, that is what we are considering, that is the first order with respect to each of the reactants. And we have also given the pre-exponential factor and activation energy for the forward and backward reaction in this particular problem statement. This is the for R plug and R CSTR. We are having a same volume of a reactor, which is 0.14 meter cube. And for this length of plug flow reactor, that is 2 meter, and diameter, that is 0.3, which is equivalent to volume of 0.14 meter cube. And feed composition that is given to us, which is ethanol, acetic acid, water. Total mole fraction, that is going to be 1, and total molar flow rate, that is 400 kilomole per hour. Now I will be directly taking you to the simulation environment. Okay. Can you see my Aspen Plus flow sheet?
Yes, Ronak,
Can
it's
I?
visible. Yes, yes.
Okay. 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 So I have just I was supposed to start it with the scratch, but I don't have that much amount of time. So I am directly into the simulation environment. So first of all, what I have done, I will just briefly tell you. In Aspen, when we are going to start with the Aspen Plus, it will ask whether which kind of flow sheet that you will want to run. So I have started with the blank simulation, and I have introduced components. So components for our case, that is ethyl acetate, ethanol acetic acid and water. So that is already available in the library of Aspen Plus. So that is what I have introduced. Then afterwards, it will ask the next step, which is what should be the property package which I need to select to evaluate all this property, because in order to simulate everything, it requires various properties such as the specific gravity, density, viscosity, all this. So it will be calculating all these parameters based on certain property package. So I have selected the Pang Robinson property package because it is most convenient for this particular kind of system. Then afterwards, I have directly come to this simulation environment. So first of all, here you can see that is at the bottom, you can see the model flags that are there. In that case, there are material streams are there. Or here also, you can also add the energy stream in the form of heat or work. Then afterwards, you can see that is a mixers, separators are there, heat exchangers are there, columns are there, reactors are there, pressure changers, manipulators, solids. If we need to handle the solids in case of a cyclone separator, then we have a different kind of modules over here. So I have started with this material stream, which is a feed, and in this feed stream, what is required. So here, when I will open this, it will ask that which kind of stream is there. So what I have selected, that is temperature and pressure, because that is already given, that my temperature that is 70 degrees centigrade, and pressure that is 1 atmosphere. Total molar flow rate that is 2000 kilomole per hour. In actual case, it is 400 kilomole per hour, as you can see over here. But I have kept 2000 kilomole per hour because I need to split it into 5 different reactors. So I will be splitting that, and the mole fraction that I have kept same, which has been already given in the problem statement. So first of all, I have defined this feed stream. Then I have selected this splitter and splitted this entire stream into equal fractions. So first, FR stoic, FR equilibrium, FR Gibbs, FR CSTR, and FR plug. So these are the feed stream to the R stoic reactor, R equilibrium, R Gibbs, R CSTR, and R plug reactor. So equally I have divided. So point 0.2, point 0.2, point 0.2, and point 0.2. So last R plug, that is by default, it will be set to point 0.2. That is the remaining fraction. So by that I have split it. So each stream now it would be having the flow rate of 400 kilomole per hour. Now coming to this first reactor module, which we are going to see, that is R stoic. So in R stoic, first of all, when we open this, it will ask this specification. So I have, as in the problem statement, it is mentioned that temperature and pressure has to be 70 degrees centigrade and 1 atmospheric pressure. And in reaction, here you can say, if I have selecting this reaction number 1, I have already, if you need to add new reaction, you can select the new tab over here, or rather, if I know we want to edit it. So here the reaction 1 and the stoichiometric coefficient, that is 1 and 1. Here you can see the minus sign is there because it is a reactants it is going to consume over a period of a time. So that's why by default, if you write 1 1 over here also, the Aspen it will consider -1 -1. And on a product side, we have a ethyl acetate and water, so which will be having a positive coefficient because they are products. Fractional conversion of ethanol I have selected as 0.7 because R stoic they do not consider about the reaction stoichiometry. So anything, if you give one fractional conversion or 0.2 or 0.5, any fractional conversion without checking the thermodynamic feasibility, it will give you the conversion. So that is what about the first reactor module, which is R plug. The second reactor module which we are going to discuss, that is this R equilibrium. So in R equilibrium, what is required in specification, again it will be asking what kind of flash type of separation you want to, or rather reaction you want to carry out. So here I have taken as temperature and pressure. Temperature to be 70 degrees centigrade and pressure to be 1 atmosphere. It is mentioned in the problem statement itself. And here the reaction which I have taken, if you need to add, you can take new, or rather if you want to add it, you can add it also. So here I have already added the components ethanol acetic acid as a reactants. Coefficient again stoichiometric coefficient, which is -1, and on the product side also there is a coefficient that is 1, 1. Here additionally it will be asking the solids if it is present in the system or not. So if the component is solid, that you need to mention as yes, but in our case there is no solid present, so I have mentioned as no. Again, for this our equilibrium, if you have noted down, it requires the stoichiometry of a reaction. So here ultimately we have defined the stoichiometric correlation between and stoichiometric equation we have fit. Then the third reactor which we are going to talk about, that is R Gibbs. So here for R Gibbs, again pressure temperature you need to decide, or sorry, you need to provide, and just that's it, because it do not require the stoichiometry of a reaction. So it will calculate the equilibrium composition based on minimization of a Gibbs free energy. So R Gibbs only requires the temperature and pressure, or you can also specify the heat duty, right? Here I have not specified the heat duty. In your case, if you are using any kind of heating or cooling medium, so you can also specify the heat duty also. Then the next reactor, that is CSTR. So CSTR here, you can see that pressure temperature again I have mentioned as 1 atmosphere and 70 degrees centigrade respectively. Reactor volume, which I have decided, which is already given in the problem statement, that is 0.14 meter cube. And here the next step, which is the reaction steps set that you need to mention. So here you can see that R1, that is a reaction set which you need to import to the next, and here also you need to specify. Here on the left hand side you can see that as the reaction folder is there, and in that I have taken this R1 set. So for this you can see that reaction, that is reaction 1, that is forward reaction ethanol acetic acid, which is giving us ethyl acetate and water. And on the second reaction, which is a backward reaction, that is the reverse of this reaction. So here I have mentioned for the first reaction. So here you can see again there are two reactions. So for the forward reaction, I have mentioned the pre-exponential factor, which is 1.9 into 10 to the power 8, and activation energy of 5.95 into 10 to the power 7 joule per kilomole. Already it is given in the problem statement. So from that only I have taken. Here you can see from here only I have taken this. Similarly, for the backward reaction also, this reaction set that has been defined. And for this R plug reactor, condition that is specified at a reactor temperature of 70 degrees centigrade, that is we want to maintain 70 degrees centigrade throughout. Then configuration also, length that is 2 meter, diameter that is 0.3 meter given in the problem statement, which will ultimately give us the volume of 0.14 meter cube. And the reaction again, which is are there in the block of R1 that I have taken. Then next you need to run this entire flow sheet. Now once this is done, then here at the bottom you can see the results are available, and you can also check the status over here. So there are no errors present. And here I have just taken this PR stoic, that is a product which is coming out from R stoic. PR equilibrium, that is a product which is coming out from the equilibrium reactor, and that is L stands for the liquid phase, V stands for the vapor phase, because R equilibrium that will calculate also the phase equilibrium. R Gibbs, R plug, R CSTR, what are the products are there, which is also are there, and here we can compare the different mole flows, or rather mole fractions. So here you can see that these are the exit composition, right? And here we can see that the R plug, we know that for any positive order reaction, the conversion for the fixed volume, that is better in case of a plug flow reaction. So here also we can see that the ethanol concentration that is in CSTR, that is greater. That means what, at the exit, the conversion, that is conversion of ethanol, that is relatively lower. So here also it is satisfying that for the positive order reaction, that the volume of, for the fixed volume, the plug flow reactor that gives us the better conversion. So this is going to be the first case study, and the second case study which I am going to discuss, that is about methane steam reforming reaction. Methane steam reforming reaction, because I have considered, because majority of the hydrogen which is produced in industry, that is by a steam reforming of natural gas, and methane, that is a major component of a natural gas. This is going to be the reaction methane plus water that gives H2CO CO2. This is what actually balanced reaction, because there are several reactions. There are around 13 to 14 reactions which are going to take place simultaneously. So this is not a balanced reactor, but these are the products which are going to form, and these are going to be the reactants which are going to take part into the reaction. So here we have given that methane and water that are available at this temperature, 40 degrees centigrade and 1 atmospheric pressure, and we need to investigate the effect of temperature and the steam to carbon molar ratio, right, on the composition of a hydrogen production. So here, just as you can see, that methane and water I have taken as a feed, taken to a mixer where these two streams are going to be mixed together, and it will be one stream, that is a feed, which is fed to a reformer, and reformer which we have selected, that is the R Gibbs, right? And here I want to explain that the effect of parameter, like say the steam reforming that is taking place in the range of 400 to 900 degrees centigrade. So every time what you need to do here, you need to go to reformer every time you change the temperature to 400 and see what will be the product composition. Then again you are going to change the temperature from, let's say, 400 to 410 degrees centigrade, and again you are observing the what will be the product composition. So here I am going to explain the importance of a sensitivity analysis. Sensitivity analysis that is going to give you the effect, right? Here on the left hand side, you can see that there are sensitivity tools. And here I have taken two sensitivity analysis. Here you can see this sensitivity block are there. I have taken two sensitivity analysis. Each steam, that is, I am varying the composition of rather steam to carbon molar ratio. That is what I am changing the flow rate of water. Ultimately, it will be changing my steam to carbon molar ratio, and I am changing also I am also studying the effect of a reformer temperature. So I am taking this two case, the effect of these two parameters on the composition of a hydrogen. So I have taken this first, what I need to in the when I have taken this. So this is what I need to vary. That is one, that is a variable I have defined. And which kind of variable is that? It is a block variable. Block variable I have taken because I am changing the temperature of a reformer. So which block variable or which block I am talking about, that is a reformer. I have given the name as a reformer. What parameter or variable I need to change, that is the temperature, and what range I need to change, that is the units. Now I have started with the starting point of 400 degrees centigrade and end point, that is 900 degrees centigrade, and it has to be equally distance, and the increment, that is 400, after that I need to keep up to 450, right? I am interested in the interval of 50 degrees centigrade. So 450, 500, 550, 600. Likewise, it will be giving us the uh, values, right? And I want to study the effect of this independent variable on the dependent variable, which I have defined as my dependent variables that are I have taken as H2CO, CO2, methane. So these are the main products which are coming out from the reactor. So first variable I have taken as H2. Which kind of variable is that? That is a stream variable, because I am interested in the product stream, how the hydrogen that is going to vary. Type, that is a molar flow rate, because I want to know what should be the molar flow rate. Product that I have taken, that is a stream, exit stream. Substream, that is mixed. Component which I am interested, that is hydrogen, H2, and kilomole per hour, that should be the unit of hydrogen. Again, the second variable, that is carbon monoxide, again the product stream, how the CO that is going to be there is going to vary. CO2, similarly CO2 and methane, how they are going to vary. And finally I want to tabulate them. So in column 1, 2, 3, 4, 5, that would be hydrogens, carbon monoxide, carbon dioxide, and methane respectively. And when I run this, So already I have run this. So here you can see that E temperature, this is the relation. See, so for the 400 degrees centigrade, what should be my hydrogen? Is this, right? And so from 400 to 900 degrees centigrade, it will give me the composition in the exit of hydrogen, carbon monoxide, carbon dioxide, and methane. So every time you don't have to introduce a new temperature, right? And see, so in a form also here, you can also see that when you vary the temperature of a reformer, how this composition that is going to be used vary. So here we can see that hydrogen that is initially going to increase like this, right? And after certain, say, temperature of 650 degrees centigrade, it is almost stagnant. So you can also decide that what should be the operating condition of your reformer. So you can see that after 650, there is no significant change in a composition. So you can keep the temperature up to 650 degrees centigrade, because going for a high temperature, it requires additional amount of heating utility requirement. Similar thing I have done for a steam to carbon molar ratio, right? In a sensitivity, again, I will show you. So what is my independent variable? That is a molar flow rate of water. Ultimately, it will be affecting my steam to carbon ratio, which I am going to vary in the range of 0 to 10 kilomole per hour, and increment that is 0.5. So first, that is mole flow of steam, which is water, and component again in a water stream, that is water, and I want to vary in the units of kilomole per hour, and I want to investigate the effect of this on again this four parameters, or sorry, composition of four components, which is H2CO, CO2, and methane. And finally, once you go to the tabulate prompt, fill the variables, and it will give us the table like this. And once you run them, it will give you the result like this. And in a summary, or in a plot or graphical manner, you can see that as the water flow rate that is going to increase, the hydrogen composition that is also going to increase. So you can again decide what should be the molar flow rate depending upon the composition which you want at the exit of a reactor. So by this, uh, I would like to invite the question from your side, if you have any.
Ronak, they will not be able to ask the questions, right?
Okay,
But
okay.
we would like to know about like how to feed the data for reaction, like because
Okay.
basic, yeah, this is everything that you have shown is very nicely. You have tried to explain all the things, right, including
Mm-hmm.
the sensitivity analysis. But if you can please quickly again show how to feed the stoichiometry data and all.
Okay, okay. So I will be taking this reaction set. So I will taking one dummy set.
Yeah.
So just I am starting with the new. Hope you can see my screen.
Yes, it's visible.
Yes. So here I am creating a new set. Let's say I'm giving my name as R2, and which kind of model, rate law model, which is a LHSW model, power law model, ionic model, which kind of model. Let's say I have this simple power law model. So I need to select this R2, and here I need to add the reactions. And for this is again, it is from the esterification flow sheet. So here on the product side, for this reaction one, I am taking this ethanol as my component reactant. Again, acetic acid as a reactant. Coefficient, that is a stoichiometric coefficient, I'm typing as 1, but by default it will taking as a -1 because it is a reactant. Here you can see that is 1 1. And this exponent, that is k, because we know that minus Ra, that is equals to k Ca raised to n Cb raised to m. So this exponent, that is what that is coming from this power law model. So in this stage, in this case, I have taken this exponent as 1 1. It is already given in the problem statement. So like this we can add. So ultimately it is minus Ra k Ca Cb. And on the product side, that is ethyl acetate, and on a water coefficient again, which I need to add, that is 1 1 over here. That is based on the stoichiometry, and exponent, that is 0 0 0 0, because it is not dependent upon the concentration of a product. So that's why I have taken as 0. Then you can click on this next button like this, and here it this set that has been added. And on the kinetics, here you can see on the reacting phase, that is liquid, there are several options are there: liquid, solid, vapor. So I am taking as a liquid. This K that is going to be, if T0 that is specified, then this is going to be the kinetic factor. T0 that is a base temperature or reference temperature rather. And if T0 is not specified over here, then you can take this equation. So in our case, this T0 is not specified over here. So K that is a pre-exponential factor. So I'm just keeping some random values right here just to explain you. And n that is 0, that is t to the power 0, that is going to be 1. And activation energy, that is again it needs to be determined from the kinetics of a reaction. Again I'm putting some random values just to demonstrate how we can add that, right? And our kinetics, that is ready over here. By this way we can introduce this reaction set also, and uh, we can take this set into so for example, if I have in the main flow sheet, if I go to this RCSTR, and now I have two sets, reaction one set and reactions two set, which just I have created this dummy. So I can take this on this side, and I can, if I don't want this reaction one set to take this, so I will be taking on this side. So by this way, I can just add the reactions. I can also introduce the kinetics of a reactions. I hope it is clear now.
Yes, yes, much clear.
Hello.
Yes, yes, Pranav, able to listen?
Hello.
Hello.
Yes, ma'am.
Yes, yes, it's very nicely explained. Yeah, another important thing that we wanted to discuss is like how to select a fluid package typically. Like what
Okay.
is the basis of selecting fluid package?
Okay, just 1 minute. I will be opening a new fresh case. Selection of a fluid package, that is dependent upon various factors, which kind of chemicals or rather reactants and products which we are using. So actually, I am also not that much because that is coming from the thermodynamics of a reaction. But Aspen has a very one tool which will help us to select a particular kind of a property package. So here, for example, I am adding components like water, and ethanol. I am adding these two components. Nextly, I will go to the next step. Here in the second tab, it will ask that which kind of property package you need to select. So sometimes it may happen that user don't have the access that which kind of property package that need to be selected. Then you can go for this method assist. In method assist, it will be asking a several questions. Let's say specify the component type, which kind of system that we are having. Let's say, for example, in our case, that is a hydrocarbon system or chemical system. Anything that we need to give certain questions, answers. Does the mixture contain the petroleum or pseudo components? If we say that as a no, then it will give us the specific, or rather it will give us the systems which we can use. So these are the systems that we can use. So accordingly, user, if they don't have the idea that which kind of property package that to be selected, so from this kind of method assist, they can get the idea. But better to have the idea about of this the packages from the literature, that if depending upon our components that to be selected, right? So accordingly we need to search through the literature and we get the idea that which kind of property package to be selected. But this could be, again, if anyone is a new, then they can have the idea that which kind of property package that to be selected. So we need to fill certain question answers and it will give us the answers. That is are the probable property package that you can select.
Okay, that will be great. I think that is not there in Aspen, not HYSIS. I've already used that.
Sorry.
Aspen HYSIS doesn't have this assistant for packet selection. I worked with Aspen HYSIS.
Yeah. So if we have this HYSIS version of this equation, means HYSIS, if you have, then you can see this HYSIS PR and HYSIS SRK.
Okay, yeah. Okay, one more question, like how to validate the results that we are getting, whether the results that we are getting are correct or are up to the
See,
mark. Yeah.
yeah, that is only by means of experimentation that we can validate. Means Aspen, that several papers are published, that majority of the times our experiment data that is matching with the Aspen plus simulation. So only the thing is that for the validation, you need to perform the experiments. Without experiments, we cannot validate our results. But majority of the times, 99% of the times, this Aspen gives us correct results.
Okay. Okay. So we are done with the questions part on.
Okay, thank you. So thank you again very much for allowing me. And once again, sorry for the inconvenience.
That was fine, but this all compensated, right? The session was really extremely nicely you conducted in such a short span of time. It was difficult to really conduct this, right? Yeah, one more thing that comes to my mind is like if we have an unknown component which is not there in the library, like what is the way of defining that unknown component? For example, a
Yeah,
hypothetical component.
yeah. So for example, you have the DES, which is a deep eutectic solvents or ionic liquid,
Yeah.
which right now in current research trend is that using that for several purposes. So we can add them as a pseudo components. Pseudo components are there. So by means of pseudo components, we can add them. But for them, we require certain additional things. For example, we require the data that how the density is going to change, how the viscosity is going to change with respect to temperature and pressure. Moreover, we require the molecular structure, this methane, water, everything that is already in the library of Aspen Plus. So we don't have to bother about what is the molecular weight and how the density is going to vary with temperature, pressure, how the viscosity is going to vary. But for the pseudo components, we need to incorporate all such data. Based on that, it will ask or it will generate the properties, required properties. So we require, for example, for a ethanol water system is there, which forms the azeotrope. With that azeotrope, that can be broken with the help of deep eutectic solvents, and several papers are also published on this particular area. So DES, they are using deep eutectic solvents. They add the, as I told, they add how the density is going to vary, how the viscosity is vary. They add the molecular structure so of the DES, right? And also it requires additionally the sigma profile. So that sigma profile and molecular structure that can be generated from another molecular simulation tools, which is a Gaussian. If you have heard about the software, which is a Gaussian, so Gaussian that gives us the sigma profile and molecular structures. And from the literature, we can identify how the density, viscosity, all such properties are going to vary with respect to temperature and pressure, right? What is the critical temperature? What is the critical pressure? All such things that we need to find out from the literature and add it as a pseudo component. Then we can use that pseudo component also, or hypothetical components, whatever you say.
Okay, one more thing. Do we have some more time with you?
Sorry?
Do you have some more time? So one more. One
Yeah,
more.
yeah, 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 yeah.
Yeah. So if you have any idea about simulating catalytic reactions, is there provision for catalytic reactor or reactor simulation?
Yes, ma'am. Yes, ma'am. So in a reactor tabs, you can see that there are several reactors are there, right? So here you in RCSTR or R plug, if you want to introduce a catalyst, then also you can introduce a catalyst also, because ultimately it will require what is the rate equation, right? And the power law model, rather than power law model, you can use a LHSW model also, which will be depending upon the catalytic, which kind of catalyst that you are selecting. So the same thing, only thing is that instead of Power law model, again power law model that can be selected for a catalyst also. So we can use this same CSTR and PF because PF, if we are considering a fixed bed reactor by with the assumption that it is flowing, the reactants are flowing in a purely plug flow manner. In that case, we can assume this plug flow reactor to be fixed bed reactor to be a flow reactor, and we can model our we can model our reactions in this R plug or R CSTR, or rather in R batch also. Only thing is that we must have the rate equation.
Okay, and any data related to catalyst, like any specific data is required related to catalyst?
Everything that is covered. For example, catalyst that alters the activation energy. So if we have the activation energy that which I have shown to you, so if you can directly feed to that.
Okay.
Activation energy. For a different catalyst, it is going to having a different activation energies and pre-exponential factors. So ultimately, the effect of catalyst that is taken care by those factors.
Okay. Okay. Okay, Rana. I think that's all from our side.
Okay. Thank you.
Yeah. So thank you, Ronak, for sparing your valuable time. Yeah, and
Thank you.
we would like to actually you be present over here with the package, right? So that our students can work with you. Right? So
Okay.
we'll sometimes plan
Sure.
definitely an offline session that will be really very much beneficial. Plus, we are also offering courses also, right? So we may invite you for some good sessions on simulation, like modeling and simulation also, right?
Okay.
Thank you.
Okay,
Thank you
sure.
very much for taking up such important topic. And again, like industry specific examples, you have shown how the simulation can be done. And the most interesting part was the sensitivity analysis that you showed, right? Yeah.
Okay.
So thank you very much, Ronak.
Thank you. Thank you again.
Thank you. Yeah. So we'll end the session. Yeah.
Okay. Bye.
Bye bye.